This video will expand on the previous video for discrete Dirac notation in terms of how we represent matrices, or how we represent operators as matrices. So if we have this operator, which is this kind of poorly drawn script O that I have, it's acting on a vector, and the result of an operator acting on a vector is going to be a new vector B. So this O is an operator, and an operator is just something that transforms a vector into another vector. Or for functions in generally, as you see in quantum mechanics, just something that transforms a function into another function. But we are representing our functions here as vectors. So we're representing our functions as vectors. We're going to represent our operators as matrices, and this video is about how that works. All right, so if we have a set of orthonormal basis vectors, I, and J is just a different potential basis vector. So we're going to have the operator O acting on I. It's going to transform I into a different vector. Whatever vector it transforms I into, we can represent in terms of the components of the basis vectors. We can do this for all I vectors, and then we know how this operator is going to act on any given vector that we give it, because all vectors can be represented in terms of the basis vectors, and if we know what the operator does to the basis vectors, then we know what it does to any vector that we give it. So this operator acting on basis vector I is going to be a sum from j equals 1 to n of some component of each basis vector j. So I gets transformed into some value in each of the other basis vectors j. Same thing for all the other basis vectors I. So we have this coefficient Oij, which is how O changes I into j. If there's no component of j in the transformed I, then this is 0. If I stays the same, then Oii is equal to 1. Okay, so O is going to be an n by n matrix representation of our operator script O. So now we define a new element of Dirac notation of the bra vector I, operator O, ket vector J. You'll see these types of symbols everywhere and often in electronic structure theory. So if you're planning to study any kind of advanced molecular quantum mechanics, prepare to see these everywhere. All right, so we know O acting on J is going to be a sum from j equals 1 to n Oij j. So that is going to equal sum over j Oij times the overlap of I and j, which is equal to a sum over j of Oij. We know that the overlap of I and j is a Kronecker delta. These are orthonormal basis vectors, so it's going to be 1. Their inner product or overlap or magnitude is 1 if they're the same. It's 0 if they're different. So this gives us 1 for the case where I equals j and 0 otherwise. So what we get is that the element Oij, the element of the matrix O in the ith row and the j column, is equal to this type of overlap here. It's the overlap of the operator O acting on j with the bra vector I. Okay, so that's for individual basis set components. So these are our basis vectors I and j. What if we want an arbitrary vector A and B? So if we want this particular Dirac overlap integral element, whatever you call it, for a general bra vector I and a general ket vector B, well, the bra A is represented as sum from I equals 1 to n of the component, the complex conjugate of its component with I and the bra vector I. The operator then acting on B, which is sum from j equals 1 to n of its component in the direction j times basis vector j. So factoring things out to neaten things up, we have the sum over I equals 1 to n, sum over j as well, of A star I, which is a scalar, can be factored out, bj, scalar, can be factored out, and then you have the bra vector, operator, and ket left. So we have then the element Oij left here, as we have defined it down there. So the result of a bra vector overlapping with an operator acting on a ket vector is the sum over I and j of the A star I component, Bj component, and the matrix element Oij. Now, if you're noticing that this looks quite similar to kind of matrix vector multiplication type formulas, that is not a coincidence, because that's exactly what they are. If we look at the overlap of A and B, the bra vector A and ket vector B, that's equal to the adjoint of vector A and vector B. So that's adjoint A times B in matrix multiplication notation. For the value AOB, that is the adjoint of A times the matrix O times vector B. So row vector A times matrix O times column vector B is going to give us a scalar as a result. Remember, a matrix times a vector gives us a vector, and then a row vector times a column vector gives us a scalar. So row vector times column vector, scalar. Matrix times column vector gives us a column vector, and then a row vector times column vector gives us a scalar. So both of these end up being scalar values. So this is how we represent our operator in a matrix form if we know what it does to given unit vectors that are our basis vectors. Then we can represent any kind of matrix any operator acting on any vector and its overlap with any other vector in terms of these types of Dirac elements.